All right, 2.5 is titled Implicit Differentiation. So I'd like to tell you that what you have been doing so far is actually called explicit differentiation. So you have been taking a derivative of y, where y is on one side, in terms of x, where all the x's are on the other side, and that's what we've been doing so far. It's called explicit derivatives. And it works pretty well when you're dealing with functions, and that's mostly what we've been looking at, right? Functions, because that's the equations that can be written as y equals and what comes next. But imagine that you had an equation of something that, man, it's not so easy to write that way. Maybe it's not even a function. Maybe even the equation of a circle. It seems like we should still be able to find tangent lines to a circle, but we have a problem because a circle doesn't have the nicest and neatest, cleanest way to be written as a function. It becomes complicated. It would at least need piecewise properties. And sometimes it's not even possible to rewrite it as y equals with x only on the other side. So when that happens, we need implicit differentiation. So this is taking a derivative of y in terms of x when the equation cannot, or maybe is messy to try, writing it in y equals form. We treat both x and y as variables. I'll show you what that looks like, of course, but we use all the same derivative rules. Okay, and we are in fact starting with a circle. Okay, so it's worth noting that I could solve this for y, but it would not be pretty. It would have a plus or a minus with a square root, right? Which makes it not a function. I'd actually have to separate it into two pieces to be able to work with it from that point, and it's just messy, all right? So I chose something to show you that that would be messy, but this one can be done with implicit differentiation, and it's really clean and nice and neat and pretty. So the first thing we're going to do is we're going to take the derivative of x squared. So what is the derivative of x squared? 2x. We know that one, no problem. Now, if you had had y squared, where the y squared is, and x squared there, you'd know again it's 2x, right? So the rules are still the same. It's 2y. But the difference is we would have to take, let me go backwards in this actually and tell you what this is. If you thought about the x squared, are y'all okay? Okay. If you thought about the x squared and you took the derivative and bring the 2 down and it's 2x, what would the derivative of x be? What's just the derivative of x? Yes, which is 1. The derivative of x is 1. Are you with me? If you're thinking about it kind of like a chain rule, the derivative of x is 1. The problem is that the derivative of y is not 1. Think about what happens when we have y equals and we have da-da-da-da-da and we take the derivative. I don't write down on the left-hand side 1 for y, right? I write what? What do I write down for y when I take the derivative? I write y prime. And there is another version of this that we're going to use. You can use y prime here if you want, but the one we're going to use is called dy dx. Okay, it's the derivative of y with respect to x. Those of you who have inderiv in your calculator, you've seen it do that, d dx on some of those. I mean, one version of it anyway. So whenever we take the derivative with respect to y, it will be dy dx. All right. On the right-hand side, I have 25. What's the derivative of 25? 0. Lovely. So what are we actually finding? Well, we're trying to solve this for dy dx when we're done. Okay? So the goal when we're done is to have the dy dx, just like the y prime, alone on one side. The catch is that we won't always be able to have just y or just x's on the right-hand side when we do that. So we can start that, no problem. We can move this so that I have 2y dy dx on the left, and I have negative 2x on the right. That's no problem. And I can divide by the negative 2y. So I have dy dx left on the left, and what's on the right? I just x over y, actually, yeah. The negatives cancel, the 2's cancel, so just x over y. So I know the dy dx part that I sort of threw in there that we haven't had before feels awkward and a little strange. But the derivatives themselves that we took were really simple. If I solved this for y, I would have a chain rule with a power 1/2. There'd be radicals involved. It would be messy. So the derivative forms themselves here are very nice. Okay, ready for another one? Let's try one. Okay. An overarching statement is we could take the derivative just like it is, just fine, and that's okay. But it'd be really nice if I didn't have a quotient on the left-hand side, wouldn't it? You with me? And because we're in control of the situation, we don't have to leave it as a quotient on the left. So what could I do to eliminate the fact that there's division on the left-hand side? Multiply by y. If I do that, I will have x plus 3 on the left. That's easy to take the derivative of. I have 4xy, and I have y cubed. The 4xy is going to be the part that's the weirdest. Everything else on this part of the problem, once I got it to this point, is very clean. Okay? Everybody good so far? If, for some reason, you're working the problem and you worked it from here, you will get the same answer. It may not look quite the same, but with some algebra manipulation, it will change and it will be the same, as long as, of course, there's no errors made in the process. And I will follow that work that you do along on a test or a quiz or something like that too, okay? But make life easy. Don't make it harder than it has to be, okay? So let's take a look at this. What's the derivative of x plus 3? 1. Right, derivative of x is 1, derivative of 3 is 0, so it's just 1. Told you the 4xy is the most complicated part. Does anybody know why I said that?
It's a product rule.
Ooh, very good. It's a product rule. Product rule. So product rule says, write the first part down, 4x, and then take the derivative of y. So what's the derivative of y? dy dx. And then I do addition. And what's the derivative then of 4x? 4. And I leave the second part, which is y, rewritten. 4y. Okay, that's the part I circled in purple. Y cubed. What is the derivative of y cubed? 3y squared. And then I have to take the derivative of the y part, which is dy dx. Okay, everybody good so far? At this point, compare this problem to the last one, which would be here. What makes the part that we're on our problem compared to the part boxed in purple here different? You have, what was it, did you say? Okay, so that's true. So what is it that's actually being done that makes the problem different because of that? Uh-huh. What's that? It is set equal to 0. That's not what I'm going for, but you're right. Say that really loud, Emma. A couple. There are 2 dy dx's. You guys see that? Yeah, and that's what you were getting at, Eric. You just weren't saying it in quite the same way. There are 2 dy dx's on this problem. Do you see that? that makes this really, there is something uniquely different about this. When I deal with this problem that's right here, this one with the dy dx's, I just shift things over and I manipulate and I move them. The problem is I have two dy dx's and they need to stay together. Okay, so you've seen this kind of algebra before, but it's not something we do just all the time on every problem. So what we're going to do is we're going to keep the dy dx's on the same side, but move everything else over. So we're going to move the 4y, so I have 1 minus 4y. And I have the 4x dy dx and the 3y squared dy dx. Okay? So everything on the right-hand side has dy dx in it. And because of that, I can actually factor dy dx out of each term. So I can write this as dy dx times 4x plus 3y squared. Why would I want to do that? Yeah, there's only one dy dx now, so now I can divide. So I have, I'll just move it on this left-hand side at the moment. The 1 minus 4y divided by 4x plus 3y squared. Okay? Okay, ready to try another one? Same directions. We have x squared, y squared, which means we have a, what rule? Product, right? It's a product. I've got two variables and they're multiplied, so it's a product rule. The first one gets rewritten, x squared. What's the derivative of y squared? 2y dy dx. Plus, what's the derivative of x squared? 2x, and then I rewrite my y squared. That's everything in purple. What's the derivative of the 37? 0. So either write 0 or just move on. And then on the right-hand side, what's the derivative of 4x? 4. This problem's easier than the last one, wasn't it? Because there's only one dy dx. So we can clean this up a little bit. I mean, as in take off the parentheses and move the 2. This is 2x squared y dy dx. And I can move my 2xy squared to the other side, so I have 4 minus 2xy squared. And then what? Yeah, just divide by the 2x squared y. So dy dx equals 4 minus 2xy squared divided by 2x squared y. Now something happens at this point that hasn't happened yet on the examples that I've shown you so far anyway. Can you see what happened? Yeah, this one needs to be reduced. The other ones didn't have that happen. They didn't have any, not all of the terms had the same thing in common on this problem, but they do here. What do they all have in common? Yeah, a 2. So when you can reduce, you do need to reduce. So this is 2 minus xy squared over x squared y. Whoops. And no set of examples would be complete without a little trig, right? Of course not. So we have an example with some trig involved. This is an interesting example because not only do we have trig involved with the sign, but the sign has something inside of it that makes it a product rule inside of a sign, and the fact that it's inside means that I have a chain rule as well. Yeah. There's a lot going on in this problem. It doesn't look like it when you first looked at it, did it? It didn't look so bad. Now it does. So we'll start by putting parentheses here. Okay, the outside function is sine, correct? So we're starting with sine. What's the derivative of sine? Cosine. Good job. And we rewrite the inside as is. This is a really good example of no matter how hard we try, it's going to be messy to try to solve this for y. It's going to be horrid, right? Because I'd have to use like inverse signs and it would be bad. It would be bad to solve this for y. And because you don't know derivative of inverse sine, you wouldn't even be able to go any further, would you? Yeah, you wouldn't. Okay, so cosine of what's inside. Now I need to take the derivative of the xy that's inside. I'm going to put a bracket so that I can kind of separate it. But like you guys said, xy is a product. So we have to use the product rule. All right, so what's the derivative of xy? X dy dx plus 1y, or y. Yeah, good. All right, but the rest of it's not bad, right? So we've got x squared becoming 2x, and then the negative 3 is 0. Good? Okay, cool. The goal is still to solve for dy dx, but the problem is that this one's actually quite messy because the dy dx is still located inside of a parenthesis with stuff being multiplied around it. So before you go any further, you can't move things to the side just yet. I mean, you could move the cosine xy if you want. So one way to do that would be to start by dividing. So if you want to do that, you could. The thing that's going to make that messy here in a minute is that I'm going to subtract the y, but then I'm going to divide by x. I'm going to have a fraction inside of a fraction. And I think most of you know by now that WebAssign does not like fractions inside of fractions, right? So this idea of dividing it initially may not be the quickest way to solve this problem. So I'm going to backtrack and show you another option. It's not bad. It's not that you can't do this problem this way. You're just going to have a lot of cleanup at the end. What I would be more apt to do would be to distribute like this to start with. So I end up with the cosine of xy times x dy dx. I'm going to put the x at the beginning and then the dy dx at the end. Not because it really matters, but that's just where I'm used to seeing them. And on the other one, I would have y times cosine xy equals 2x. So that's what the distribution step would look like. The piece that doesn't have dy dx now can move to the other side just fine. So I've still got here x cosine xy dy dx, and then this would equal 2x minus y cosine xy. And then what will we do? Divide. Yeah. So dy dx would equal 2x minus y cosine xy over x cosine xy. Okay. The other one will work the same way. You'll just have more cleanup at the end to get common denominators and to simplify the double fraction business if you do it the other direction, okay? Any questions on that one? Our directions are about to change a little bit. Okay, let's take a look then. We're going to find dy dx by implicit differentiation like we've been doing, and then we're going to evaluate it. Do you guys start to feel like every single lesson I teach you is the same? I teach you how to do the calculus, and then we plug in a number, and then we create lines. Yeah, that's actually exactly what we're doing. So we're going to do it again. We're going to find dy dx. So on this one, over here, we again have a product, right? Got a product. And inside of the cosine is a y, which means that's parts of chain as well, because y is inside of cosine. So we've got a little bit of weirdness going on there. parentheses. The question is, do I have any required parentheses if I were to put it in a calculator? Yeah. All right. What's the derivative of x cosine y? You can always start. Starts with x, right? And then what's the derivative of cosine? Negative sine of y times dy dx. Yeah. Okay, that's half of it, plus, good, cosine y. Yeah, 1 cosine y or cosine y, either way. Yes, equals 0. Honestly, the only simplification that I would do, if it were me, is move the negative to the front before the x, and I'd plug the number in, because that's where I'm really headed in this problem anyway, is to evaluate it. I don't really want to clean up a lot of algebra that's messy. I would love to clean up algebra that has the values in. Now you'll notice it is actually really important on this particular problem. They gave us x and y, and that's good, because we need them both, right? Because we have an x and a y in our problem. So we're going to plug in both of them at the same time. So I'm going to put my negative at the beginning. X is 2. Sine of y is pi thirds. And I do have the dy dx here that I'm finding, right? I'll solve for that in a minute. And then I have cosine of pi thirds. And this is probably one of the first times, at least in class, that I've asked you to remember some very specific trig function evaluation. So pi over 3, that's a value on your unit circle. You are welcome, by all means, to have a unit circle handy when you're doing your homework and so forth, if you don't remember it. But we do need to know what the sine of pi thirds is and what the cosine of pi thirds is on this problem. So do you remember the sine of pi thirds? Sine is one, it's, yeah. Yeah. One of them is radical 3 over 2, and the other one's 1/2. You just have to figure out which one it is. Yeah. So sine is the square root 3 over 2. And cosine is 1/2. And if trig's been a while, or if you're rusty on that and you want to come chat with me a little bit about that and remember how to do that, come do that. I'm happy to do that with you one-on-one. We can take a look. Our goal is to solve this for dy dx, so we're going to clean things up a little bit. This is actually really nice that these 2's cancel. So I have negative square root 3 dy dx equals negative 1/2. I'm going to divide by the negative, sorry, look at my paper funny. I'm going to divide by that negative square root 3, but that's the same as multiplying by the reciprocal, like 1 over square root of 3, which is a little easier to deal with because I've already got a fraction over there. So I'm going to multiply by negative 1 over square root 3. So I have dy dx. It is positive. I end up with 1 over 2 square root 3. But you do remember from trig that you can't leave it like that, right? We don't leave radicals with numbers, right? A radical that for sure is irrational in a denominator. So we'll rationalize. So we end up with square root 3 over 6. Okay, so you'll notice that the directions on this problem, unlike the last sections that we have done, at least at this point, don't say verify with nderiv. You could still verify this with nderiv, right? The thing that nderiv won't do for you is give you a form that looks like square root of 3 over 2. It will give you a decimal approximation, but you could take your calculator and you could actually plug in square root of 3 over 2 and find the decimal approximation version of that too and compare them. Yes?
So it would be okay if, like, where you plugged everything in, I moved it over and then
Yep.
you had dy dx.
Absolutely, it would be the same thing. Yep. Okay, any questions on this one? Okay. See if we can finish our last 2 problems up. Find an equation of a tangent line to the graph at the given point. And then it says graph the tangent line in the same viewing window. Now the reality is that this problem is a what? Like, what is this equation? It is a circle. So I actually think that you could probably roughly sketch this without your calculator easier than with your calculator. Because your calculator doesn't graph circles all that well. You have to solve it for y, and that would be messy on this particular problem. So if you'll remember from what you know about circles, the center of a circle is hinged on those values that are beside x and y. So the center of the circle, we're going to do this sort of out of order, I guess, since I've started the process, is at -2, 3. And do you remember how to find the radius in that form?
Square root of 37.
Yeah, it's the square root of my 37. So what is that approximately?
Great question.
Great question.
6.
Yeah, it's approximately 6. Very close, because square root of 36 would be 6, right? It's about 6. So in terms of graphing, we're going to graph the center at -2, 3. And we're going to go out about 6 in all directions, in particular in the directions left, right, up, and down from there. It is a sketch, so the fact that it's not exactly 6 is actually really not a big deal at all. Okay, it's not perfect, and I cheated some too because I have a circle tool and you don't. I'm sorry about that. We've got an approximation. All right, so there's my circle. Let's go back and actually do the calculus for this now. Implicit differentiation to find the derivative. So x plus 2 squared is a chain rule, right? Like the ones we were dealing with before. So I have 2 times x plus 2. And it's times 1 because the derivative of x plus 2 would be 1 plus 0. And then on my y minus 3 squared, I have 2 times y minus 3. It would be to the power 1. And then what's the derivative of y? dy dx. And then minus the 3 would be 0. And this would equal 0. All good? Nice. We are going to evaluate this at the x value of 4, the y value of 1. We can plug those in right here, or we can simplify either way. Here I have 2 times x is 4, so 4 plus 2, plus 2 times, and y is 1. Is that right? Yeah, 1. So I have 1 minus 3. dy dx equals 0. On the first half, 4 plus 2 is 8 times 2 is 16. 1 minus 3 is -2 times the 2 would be -4. Thank you. I did multiply instead of add. You're right. Thank you. Equals 0. So if I solve, what will dy dx be? Three. Yeah, it's 3. Move the -12, or the 12 over as -12 and divide by -4. I need an equation of a tangent line. So I have y minus y1, which is 1, equals m, which I just found 3, times x minus the x value, which was 4. This is y minus 3x. I have minus 12, and then I have plus 1. So 3x minus 11. And I'm going to just graph it on my on my screen that I've got here with you guys. But 3x minus 11 will end up being over here at the point 4, 1. So we said 4, 1, which would be about right here. And this ends up being roughly like this. That is not the best sketch ever, but it could be worse. All right, I have two options which we're going to decide really quickly. You can give me 2 more minutes to finish the next one, or you guys can head out. I'll stay in the room and record 2 more minutes on my own, and then you can watch the 2 minutes later. What do you want to do? Want to stay here? Let's do it. Okay, head on out, Maurice. You can watch it later. All right, my last question right here. I need you to know what this notation means. This notation means second derivative. And all a second derivative is the derivative of the derivative. That's it. So it means we're going to do the process twice. What's the derivative of 2x? I'm sorry, of x squared. I'm trying to get you out of here. All right, what's the derivative of y squared? 2y dy dx. And the derivative of 36? 0. I need to solve for dy dx before I move on in this one. I have to, all right? So on this one, I will have negative 2y dy dx. I'll move my negative 2x over and divide dy dx equals, oh, I forgot that part of it, over negative 2y equals x over y, yeah. So that's my derivative, which is the first problem I already did today, actually, on this lesson. And then we're going to take our second derivative. This is read the second derivative of y with respect to x twice. That's why the 2's are where they are. It's a little weird, but that's how it's read. And we haven't done a quotient rule today, so this is so good. We get to do one. The derivative of x over y is the quotient rule. So we've got the denominator times the derivative of the numerator plus the numerator times the derivative of the denominator, which is dy dx, all over the denominator squared. But here's the thing. You know what dy dx is.
Is it minus?
It is minus, whoops, I didn't get that erased. Yes, thank you, Emma, it's minus. You know what dy dx is. It's x over y, isn't it? So we have to plug that in. So I have y minus x times x over y squared. Fraction inside of a fraction, which is sort of unfortunate, but we can do that. So I have x minus, well, let me get the fraction, do the same thing again. This would be y squared minus x squared over y squared. And I can multiply by the reciprocal. So we end up with y squared minus x squared over y cubed. There's one more cool thing. One more really, really cool thing. Do you notice what that numerator is? It's almost the same thing we started with. If x squared minus y squared is 36, what is y squared minus x squared? Negative 36, that's right. So we thought we were done. It almost looked like we were, and in many cases we would be, but on this particular problem, it is negative 36 on top over the y cubed on bottom, and then we're done. It's not going to happen real often, but when it is, you have to notice it. All right? I'll see you guys on Monday or Tuesday. Remember, gateway quiz, regular quiz, and it tells you in the syllabus what the regular quiz is over. I can't remember, so let me look. It's over 2.3 through 2.5, so it will have, I think it has one question from each section on it. Okay, 2.1, 2, or 2.2, 2.3, 2.4, and 2.5.